Hello everyone, welcome to Digital Lesson for Students by Department of School Education, Nagaland. I am T. Pungudi, MSc MPhil Mathematics, your math tutor from C.D. King Higher Secondary School, Science Stream, Jotsama, Kohima. In the last session, we learned the definition of differentiability. Let us have a small recap on it. Let fx be a real valued function and a be any real number, then fx is differentiable at x equal to a if limit fx minus fa by x minus a, where x approaches a, exists and it should be finite. And we have seen how to find the left derivative and the right derivative as well. In this session, we will start with the geometrical interpretation of derivative of a point. Geometrical interpretation of a derivative. You might have studied already this in class 11. Let us have a small recap on it. Okay, let me take a graph, the curve y equal to fx. Right. Suppose if we get the curve like this, okay, this is y equal to fx, the curve. And let me take a point on the curve P. Let it be the x coordinate is a, then automatically the y coordinate will be fa. So a, fa, right? And I'll take one more point in the neighborhood of P. Let it be q. So it is in the neighborhood. That means the distance is very less. So it is at a distance of h from here, a. So that x coordinate will be a plus h, then our y coordinate will be f of a plus h. Alright, so this point is a and this point is a plus h, and what it will be this distance? This will be h again, right? Okay, and we will draw a secant or chord, it's up to you, whichever you want to remember. So secant, it passes through like this, the secant. So it passes through like this at this point. Fa. Alright. So let us write the slope of this secant. Slope of this secant. Slope of the secant PQ. It would be, if you use that slope formula, y2 minus y1 by x2 minus x1, that is also okay. If you want to use the tan theta, that is if you take this one as theta, then the perpendicular by base, that also you can use it. Both if you will get as fa plus h minus fa, y2 minus y1 divided by x2 minus x1, that is a plus h minus a. So a gets cancelled, you will get h again. Alright. Now, what are we going to do? Let us bring this y point, q point closer and closer to P. Slowly we are moving this point Q towards P. See, it will reach here, then if the Q comes here, then the secant will go like this, right? And if it comes here, then again the secant will go like this. And if you move here, the secant will move like this. And then slowly when it comes here, then the line will pass through like this. So what is this? It becomes a tangent, isn't it? Okay. When we move this point Q towards P, what will happen to this H? This H will move towards, approaches 0. Yes or no? The distance becoming 0. Alright. So that means when this limit or LT or LM Q approaches P, I put plus because it is the right side. Similarly, you can take a point on the left side also. So, slope of the secant PQ is equal to, when Q approaches P, here this H approaches 0. So in this case, fa plus h minus fa by h. Okay. So when this q move towards this p, the slope of this secant becomes slope of the tangent. Therefore, this is slope of the tangent at p. This is limit h tends to 0 fa plus h minus fa by h. Okay. And what is this? This is our right hand derivative. In the previous session we have seen, if you replace x with a plus h, you will get that one. Alright, so this is equal to f dash of a. Right, so the slope of the tangent at p is nothing but the derivative of the point, derivative of the function at that point. Okay, so what can we conclude? The geometrical interpretation of the derivative is the derivative of a function f at a point is nothing but the slope of the tangent. Slope of the tangent, that is also unique, very important. Only one tangent we can draw. Unique of the same function of the curve y equal to fx at that point. Right? The derivative is nothing but slope of the tangent. This point we need it for the application of derivatives. Please remember this one. So from the geometrical interpretation, we learned that the derivative is nothing but the slope of the tangent at the same point. Alright. Next we will move on to relation between continuity and differentiability. Okay, now relation between continuity and differentiability. If a function, first of all let us prove that differentiable function is continuous. Alright, if a function f is differentiable at a point A, then it is also continuous at that point. Let us prove this one first. Since f is differentiable at A, so we get f dash of A is limit, by definition, x tends to a fx minus fa by x minus a. This limit will exist, right? And it is also equal to a finite value. Alright, okay. At x not equal to a. At x not equal to a, what do we have? Fx minus fa, we can write this one as fx minus fa by x minus a. I multiply and divide by x minus a here. It can be written like this, at x not equal to a, isn't it? Now let us take the limit x tends to a, both sides. We have already studied the algebra of limits in class 11, so we are going to use that. So limit x tends to a fx minus fa by x minus a into x minus a, we get like this, right? And then when you apply the algebra, we can apply the limit separately. Limit x tends to a fx minus limit x tends to a this is a fa. This will give us limit x tends to a fx minus fa by x minus a into limit x tends to a x minus a. Alright. Now how do we apply the limit? The first method is direct substitution, isn't it? When x is approaching a, we can replace x with a. So a minus a becomes 0. So this becomes 0. So automatically the right hand side will become 0. So this limit x tends to a fx minus, here x tends to a, fa will remain the same, right? Fa only, there is no x term here, so fa only will be here, and this is equal to 0 because this value is equal to 0 when the limit x tends to a. So this gives us limit x tends to a fx is equal to FA. So this is the definition of continuous, right? So when we take a function is differentiable at a point A, so we can come to the conclusion that it is continuous also, isn't it? Since A is arbitrary, F is continuous everywhere, right? Continuous everywhere. So with this, we can conclude that every differentiable function is continuous. Every differentiable function is continuous. Okay. And what about the converse? Every continuous function is differentiable. Let us check it out. Let me take a function, continuous function, that is fx equal to absolute value of x or modulus of x. We know that it is continuous everywhere, right? So let us find out at x equal to 0. Okay. So how do we define fx, that modulus of x, which you have learned in class 11? This will be equal to x for x greater than or equal to 0 minus x less than 0, right? So when it is positive, we take x as it is, positive and equal to 0. But when x is negative, we will multiply with minus again to make it positive, isn't it? That's why minus x less than 0. Okay. Let us show that first this is continuous. So for that, right hand limit and left hand limit. So limit x tends to 0 because we are taking at that point x equal to 0. 0 minus, this is left hand limit. So this is equal to limit x tends to 0. Left side of 0 is less than 0. So the function is minus x. So minus x. So if you give the direct x equal to 0 substitution, you will get 0. Isn't it? Then let us find out the RHL, that is right hand limit. So it will be limit x tends to 0 plus fx, that is equal to limit x tends to 0. Right side of 0 is greater than 0, right? So this is x. So here also when you give x equal to 0, it becomes 0. And what about f of 0, that is at x equal to 0. So that is also at x equal to 0, it takes x, isn't it? So this is also 0. So all these three are equal. Therefore LHL is equal to RHL, that is equal to f of 0. Therefore fx is continuous, that is fx modulus of x is continuous at x equal to 0. Okay, it is a continuous function at x equal to 0. Now let us find out whether it is differentiable or not at the same point at x equal to 0. Okay, so first let us find out the right hand limit or left hand limit, it's up to you. Rf dash of 0, that is equal to limit x tends to 0 fx minus f0 by definition by x minus 0, isn't it? Okay, fx is, this is the right side of the limit, therefore we take x, isn't it? So limit x tends to 0, fx is 0 because right side of 0 is greater than 0, that is x. So 0 minus, let me take x first, x minus f of 0 is 0 by x. Okay, so x minus 0 is x, x minus x is 1, isn't it? Therefore it gives us 1. Okay, then what about left hand limit? Limit x tends to 0 fx minus f0 by x minus 0 will be limit x tends to 0. Left side of 0 is minus x. Therefore minus x minus 0 by x. So when you cancel this, you get minus 1. See, this is not equal. Different. RHL is not equal to LHL. Therefore it is not differentiable. LHL, LHD, differentiation, right? Derivative. RHD not equal to RHD. Therefore fx equal to absolute value of x is not differentiable at x equal to 0. Okay. So by just showing an example, we have proved that the converse is not true, right? See, we have taken a continuous function, but it is not differentiable. Even if it fails in one case also, we can say that that statement is not true. Therefore, a continuous function need not to be differentiable. Need not to be differentiable. Differentiable function. So you might get this one for your 2 mark or 4 mark. Prove that a continuous function is not differentiable. Okay, in that way also the question may come. Otherwise, in MCQ, fx equal to absolute value of x at x equal to 0 is option A, continuous but not differentiable. Option B, not continuous, neither continuous nor differentiable. Continuous and differentiable. Right? Similarly, you will have more options. So in that type of also it comes. So take note of this. This is very important. Often asked this question in your question papers. Okay. Algebra of derivatives. Okay. Let me take u and v, two functions, u and v as two functions. Then u plus or minus v whole dash. If you are finding the derivative of u plus or minus v, then you can find out like u dash plus or minus v dash. Separately you can find the derivative. Both will be equal. Then the second one is when you multiply a function with a scalar and if you are trying to find out the derivative, this is equal to lambda u dash. Lambda is a scalar here. Okay, you can take that scalar outside and then you differentiate only the function. The third one is product rule or Leibniz rule. It's the name of a mathematician. Product rule or Leibniz rule is u v whole dash. When there is a product of two functions, then how should we find out the derivative? So we cannot directly see it is not equal to u dash v dash. It is not correct. So most of the students, they do these mistakes. So it is not equal to u dash v dash. It should be u v dash plus v u dash. That means you keep this, any one of, you can do it v u dash plus u v dash also, no problem. You keep it constant and find the derivative of v, and then keep v constant and find the derivative of u, and you have to add these two. And the fourth one is quotient rule. Quotient rule for division. So there is u by v whole dash is equal to v u dash minus u v dash by v squared, provided v not equal to 0. Okay, this is quotient rule. When there is the functions are in division, then we have to apply this formula to find the derivative. Okay, these are the algebra of derivatives. We will be using this for our chain rule that we are going to see in the next session. Thank you.